Can you hear me back there? Apparently, the mics that pick up the streaming work, but the other ones don't, right? But we had a long week last week, so I'm about to, the voice is kind of going in the other direction right now, but I hope you can hear me. Great to have you all here this afternoon, and I, certainly appreciate everybody here, faculty, staff, students, friends, and visitors, because I'm welcoming you to the 38th Reynolds Tobacco Company Award ceremony and lecture. Now, we don't have a representative from the Reynolds Company here today, but the Foundation Board, the Engineering Foundation Board, is a partner in this event. And I'm delighted that David Whitley, who is head of our development committee on the Foundation Board, David, if you could stand up, okay, is here today. So thank you very much for your support. The Reynolds Tobacco Company Award for Excellence in Teaching, Research, and Extension was established in the College of Engineering to honor a member of the engineering faculty who has demonstrated superiority in several areas of activity that relate to the university's threefold mission of teaching, research, and extension. This annual award is supported by the Reynolds Tobacco Company, again through the NC State Engineering Foundation, to bring recognition to scientific and educational achievements in fields of engineering. A committee of engineering faculty members representing academic, research, and extension areas, as well as representatives from other university colleges, review the nominations and recommend a candidate, in this case to the dean. And the following criteria are used in the selection of the candidate: contributions to education, scholarly activities, extension, and public service activities. And then the award recipient is asked to prepare a lecture on a topic related to engineering, and that's really the key part of today. This is a $25,000 award. It's awarded in increments of $5,000 over a 5-year period. It is the most prestigious award the college presents to an individual faculty member. Now, we have previous recipients of this award here. Some of you who are still in the link to have monetary compensation for this, right? So I'm going to start with that, and then I want to make sure we recognize all the others. Now, you're going to find this interesting. In the previous years, we would present a check to the previous awardees, but now, John, it's all direct deposit, right? And I'm going to preempt this a bit. The first previous recipient that I saw a little bit earlier today was Jan Genser. And I said to Jan, I said, no checks today. Think about that a moment. Jan is from Czechoslovakia. John looked at me and said, am I not supposed to be here today? Like what's going on here? You definitely are, yeah, definitely are. First of all, let me start with Michael Dickey. Michael Dickey, Camille and Henry Dreyfus Professor in Chemical and Biomolecular Engineering. Michael was a recipient last year, so Michael, that direct deposit is going to come in. This is for year 2. Where is Michael? Michael's here? Yes, please. Stay standing. I want all you guys to stay standing. Jacob, you're here. Jacob Jones is next to Michael, Distinguished Professor in Material Science and Engineering for your 3rd year. As I mentioned previously, Jan Genser. Yes, Jan. Frank and Doris Culberson, Distinguished Professor in Chemical and Biomolecular Engineering. This is 4th year. And I don't see Richard Kim here. Is there anybody from Civil Engineering? Well, Richard Kim, Jimmy Clark, Distinguished Professor, University Professor, this would be his year 5, okay? Now, there's other previous recipients of this award, I believe, here. And if any of you are here, please stand up. Carol, you're a previous recipient, right? Okay, and Hal? And Saad, okay. Anybody else? Okay. But no checks for you guys now. You're beyond that. Well, thank you all for being here. Now, at this time, I'm very pleased, actually delighted to recognize this year's recipient, Dr. Richard Spontak. Dr. Spontak, Distinguished Professor of Chemical and Biomolecular Engineering, came to NC State, arrived in 1992. So you're talking about 3 decades with us here. As a professor, he's known for his vast contributions to his discipline while making a difference, a significant difference in students' lives as a mentor and teacher. In the world of polymer science, Rich is widely recognized as a global leader in nanostructured polymer systems. One of his pinnacle achievements lies in the application of electron tomography to study the 3D characteristics of nanostructured polymers at nanoscale resolution. Rich's research has yielded over 300 peer-reviewed publications, 6 patents, over 350 invited talks, 32 international journal covers, and 1 book cover. His impact is quantified by well over 15,000 citations, an H-index of 62, with 11 papers cited over 200 times. That's a phenomenal record, Rich. Rich's transformative discoveries and identification of solutions to contemporary problems have been recognized through multiple honors and awards over the years, but most recently, in this last year, he received the 2022 NC State University Alexander Quarles Holiday Medal, which again is probably the highest recognition we have across the university. He also received in 2022 an international award from the Society of Polymer Science in Japan, and the 2022 American Chemical Society PMSE Division Roy W. Tess Award in Coatings. 2022 was a banner year, right, Rich? Rich is a member of 9 different professional societies. He's a fellow of the American Chemical Society in the Polymeric Materials Science and Engineering Division. He's also a fellow of the Institute of Minerals and Mining, a fellow of the Royal Society of Chemistry and the American Physical Society, as well as a fellow of the American Association for the Advancement of Science. In addition to his tremendous research productivity, Rich is considered by many engineering students and faculty members to be an outstanding teacher and mentor. He creates a welcoming environment for his students and enhances their learning through introductions to other world-class faculty members and exposure to interdisciplinary research. His honors related to that include the 2008 NC State Board of Governors Award for Excellence in Teaching and the 2021 Tau Beta Pi Engineering Honor Society Distinguished Alumnus Award. Rich, let me offer you simply my sincere congratulations on this very well-deserved honor. Now, the way this usually is that you would come forward and I'd give you a certificate and a check, but there's no checks today, right? But we do have a certificate, do we, Tracy? There you go, okay. And the check is not in the mail, it's electronic, right? But let me do that. So Rich, if you could come up here a second. There you go. Brent, you probably want to take a photo. Let me read this now, okay? The R.J. Reynolds Tobacco Company Award for Excellence in Teaching, Research and Extension to Richard J. Spontak in recognition of scientific and academic achievements in the field of chemical and biomolecular engineering. Congratulations again, Rich. Okay.
Thank you so much.
You want me to keep it for you? Right here. Okay, and now I'm going to turn it over to Rich, and you're going to give us your lecture. Thank you very much.
Thank you so much. Thank you so much, Dean. Appreciate it. Thank you. I'm not quite sure how to start after that. That was really wonderful to hear. Thank you. Well, let me begin by, first of all, expressing my great gratitude to all of you for coming today. It's a real pleasure for me to be amongst good families, friends, colleagues, and many of you I really owe a debt of thanks. So let me begin, before I get too choked up, to talk a little bit about the presentation regarding my research. So you'll notice under the main title, I added "Just Add Water." That is because of Matt Shipman, who a couple of years ago sent out a press release on one of our works and said, "Oh, you only have to add water to these?" And I said, "Yes." He said, "You mean it's kind of like a cup of noodles?" And I thought, yeah, kind of like that. So I figured, okay, we'll start with that. Now, I'd like to begin, and you may have seen this as a preview, but I really want to dedicate this award. It's not for me. It really isn't. It's for the students with whom I've had the pleasure to work, and with my colleagues with whom I've had the pleasure and honor to work. So let me point out the students who've contributed in some way to this particular presentation. You see them listed here from NC State, and the 4 who've contributed the most are shown here in pictorial form. Bharadwaja, Wade, Jachi, who is with us today, and Kenny. And then there were a couple of students from the Norwegian University of Science and Technology who also deserve credit. And so I've listed them as well. I also have to, of course, point out finances. So you can see here the organizations who have contributed to this work at some point during the research. And it's been a pleasure to work with all of these institutions throughout the years. So, you might be wondering why Michael is up here. I wasn't kidding when I told you, Michael, that you were playing an important role today. Because when you gave your presentation last year, it was inspiring. You told us how your Wolfpack family really guided you in your journey here. And it was really a wonderful thing to listen to. So I started thinking, how on earth am I going to follow up on that? And I thought, well, we're getting close to the holiday season, and so maybe I should think of that as a way to tell stories. And then I thought, no. I would give my wife too much opportunity to remind me that I have to lose weight. So then I thought a little bit more, and well, for those of you who know my deep passion for a particular fantasy genre, I thought, yeah, we're going to go with this. And you don't know how much time it took to match my face to Gandalf's face. Well, I thought, okay, I'm going to tell just a little bit of a short story. So allow me just a few moments to give you some context for how I got here. So if you look at the bell tower, we're going to turn those hands of time back just a little bit. And I'm going to start at the beginning. No, this does not start with my birth. But it is going to start with what made me into the person standing before you today. So I grew up in a small town. It was about 4,000 back then. It's now down to 2,700. And it's probably going to continue dropping. Biggest claim to fame, a book that deals with the primary economy, coal mining. My father was a coal miner. My uncle was decapitated coming out of a coal mine. So it is deeply ingrained in my blood. And more importantly, we were only about 30 minutes from Mrs. T. Pierogi's manufacturing site in Tamaqua. Or, if you're not familiar with that, think about Yingling beer. And so we were about 20 minutes from the oldest brewery in America. But the most important thing from my perspective was this small town wasn't unlike a lot of small towns here in North Carolina. There were lots of similarities. And so if we start moving on a little bit further, yeah, there were several firsts that I had. You might remember an article written about the spelling bee. Yeah, I was the first one from my high school to get there. And yeah, that's my mom who almost knocked me off the stage when I won. Please do not ever mention the word Replevin to me. I still will break out in a cold sweat when I hear that word. That's the word I lost on. Then I had my first publication, right here, the U.S. Congressional Record. It was a poem about U.S. history and the importance of democracy. Gee, does that sound familiar? And then lastly, I was the first one in my family to go to college. And I relate very much so to a number of North Carolinian students who come from the same background. And so it's very important to give them all that they need to succeed. So, a couple of important points along the way. At Penn State, a professor by the name of Mike Cardamone was a physics professor who could make any physics problem the most interesting problem in the world. In fact, they weren't problems to be considered in homework sets. They were challenges that you could mount your life's career on because they were so fascinating. And that kind of curiosity just impassioned everyone. Robert Cable, person that I don't mention very often except for the fact that he believed in me. He allowed me as an undergraduate to teach several of his courses in reaction engineering, which was very unusual at the time. And that kind of opportunity just gave me so much confidence to be able to basically carry on. Then we go to Berkeley. And I'm not mentioning my advisor here because he wound up helping me, of course, with a PhD, but rather I'm mentioning John Prosnitz because he wound up on day one when we arrived, when my cohort arrived, and told us, if you're here as a graduate student to make money or to pursue fame, leave now. And those words have stuck with me all these years. Instead, they've actually added to my own personal credo of what I believe I should be doing as a faculty member. Alan Windle at Cambridge, he basically showed me that I could do what I thought was impossible. And he demonstrated to me how important it was to never give up simply because something was incredibly difficult. And then lastly, the two people who were with me my entire life, my father and his brother. I went back and I found their old service pictures because that's what I always remember them for, their service. They were part of the great generation. And what you see here is a person who had an incredible moral compass. And I only hope I could practice a tenth of that. My uncle, he was the engineer. He was the one who inspired me to pursue engineering to begin with. And so I really can't express the gratitude for these people. Now, well, I have a lot of other people that I really am grateful for. So if you look carefully, for those of you who have collaborated with me, you'll see your picture showed up here. Okay, and I owe all these people a great debt of thanks for enriching my life, for helping me to learn, and for trying to push the envelope, to try to engage in discovery. And that's, I think, the real meaning behind think and do the extraordinary. So with that said, let me get back to water, because it's playing an important role in what I'm going to be talking about today. And I'm going to start actually with a tangential topic, which is climate change, because we all know how important it is. In this chart, you can get an idea of why 2050 is being, or 2040, excuse me, is being identified as the break point for the 1.5 degrees centigrade global increase in temperature. It's just a linear extrapolation of the current data sets. Where do most of these emissions come from? From fossil fuel power plants, from the cement industry, from the steel industry. If you start looking at what appeared last year in Nature Review, you'll find that this dotted curve right here corresponds to CO2 emissions, and this is CO2 plus methane. We're right in here, and the predictions for us to be able to get to 1.5 degrees centigrade increase in temperature is shown here. That's that very, very steep drop. If we want 2 degrees, well, we have a little bit longer to extend that out. But the point is that while new technologies are being developed, and rightfully so, to harness clean energy, alternative energy sources, we can't just give up on fossil fuel. In fact, if we start looking at carbon emissions throughout the US, came out from EPA last year, you'll notice that there are still considerable emissions from the Rust Belt and of course from the Deep South, including the petrochemical industries in Texas. If you look at North Carolina, we're not that bad, but we could be doing better. And we have to realize that that becomes important. It's not going to be an on-off switch where we suddenly go from petrochemicals to an alternative energy source. We do need to realize it will be gradual. And so, if we don't take this seriously, well, we have already seen the outcome. We've already seen the forest fires in the western part of the US, throughout Europe, throughout Australia. We've seen regions go from reasonable agriculture to drought, which could introduce geopolitical instability. And on the other hand, we can go the other direction and talk about the floods of Pakistan. Or we could be talking about superstorms in general, affecting not only North America, but also East Asia, and of course, the polar ice caps melting. So we know the outcome. Now the question is, what can we do about it? Well, before answering that question, I'll pose that there are other reasons why we want to consider capturing CO2. One is we can better harness our natural resources, like methane. This process is called methane sweetening. Or we could start purifying hydrogen, since CO2 is often a residual diluent in hydrogen production. So this is just making fuels better. But we could also be thinking about air purification. Why is that important? Because we have great aspirations of trips to the moon, trips to Mars, colonies, etc. And so we have to be thinking about air purification in a much more efficient manner. But we could also be talking about aquaculture and as a new source of food supplies. So we have a lot of driving forces for us to consider removing CO2. The last one, well, we've all seen enough pictures of these for the last couple of years. And when you start considering that the tubing on a ventilator is intended to remove CO2 as well as recirculate oxygen, there's another driving force for us to consider how to capture carbon. Okay, so, Hal, please forgive me, but I got to digress for a moment and just tell you a little bit about transport and polymers, because it's an important thing to understand. And I'm going to keep this very, very brief. There are two important parameters that we need to know. One is the permeability, which is how much of a penetrant gas makes its way through the polymer. And the other is the selectivity, which is the ratio of permeabilities. So it tells us the quality of the separation. This is the metric that we're going to use for comparison purposes. It's called a Robeson plot. So on this, we're going to compare selectivity of CO2 to some gas. We normally choose nitrogen as a surrogate for air, and we have it plotted against CO2 permeability. Notice it is on dual logarithmic coordinates, and there are 2 lines on it. Those lines are referred to as the Robeson upper bound in honor of Lloyd Robeson. So, what this means, very simply, is if you wind up producing a material, a membrane, that allows for high permeability, well, pretty much everything is going to go through. So selectivity is low. If, on the other hand, you develop a membrane that is highly selective for one particular component, like CO2, then chances are the permeability is going to be low. And so this is a trade-off. And the reason why there are 2 lines, one is that the black one is the original, and the red one is a more recent version of this. And you'll see this again a little bit later. Okay? Lastly, mechanisms. How does transport occur? One is by a mechanism called solution diffusion. This is the most common of which, and it really says that the permeability depends on 2 components, the diffusivity and the solubility. So the selectivity overall depends on the diffusion selectivity and the solubility selectivity. The second mechanism, which is not all that common, is called facilitated transport. And this is basically reaction-augmented diffusion. So in most cases, we will have one or the other, solution diffusion or facilitated transport. And in the former, we have either diffusion control or solubility control. If it's diffusion control, we say it's size selective. So think of this as basically using a strainer and allowing small particles to get through easily and keeping the larger ones from getting through so easily. On the other hand, reverse selective simply tells us that we're actually going to allow larger molecules to get through faster than smaller ones because they are more soluble in the polymer. Okay, so that's the background. I promise no more on that. So now let's look at a little bit of what led up to a major find that we had. It started with a study about Nafion. And for those of you who might not be familiar with Nafion, it's commonly used in fuel cells. It's a very expensive polyelectrolyte that has both charge to it and highly, highly hydrophobic units. And what we thought was because it has these charges due to sulfonic acid groups, we could simply introduce an ionic liquid into this, which has a positive charge, so that we could broaden these small channels, and then we could introduce water vapor to broaden them more. Now, how big are these channels? This is a TEM, a 3D TEM image that was published by the National Center for Electron Microscopy in California with regard to Nafion, and those black regions you see there, those are the hydrophilic channels. They measure just a couple of nanometers across. So really, really tiny, where a nanometer is 10 to the minus 9th meters. This is the ionic liquid we're using. It is quite easily used in conjunction with water. And so the result of this was surprising for us, because not only did the addition of the ionic liquid increase the CO2 permeability, well, ionic liquids have a nice affinity for CO2. The solubility of CO2 is high in them. But when we started introducing water vapor, just as we had hoped, we were starting to track an increase in the CO2 permeability. And that was basically telling us that we could use water vapor as a way to get an idea of how CO2 would proceed. Well, if that worked, why couldn't we make the channels bigger? So this is where we started thinking about block polymers. In this case, these were charged. So this is the chemical structure, and the only thing that you need to know about it is that here's the charge segment. There's the sulfonic acid group, and this by itself will form spontaneously a nanostructure that depends on what solvent is used for casting. So if it's cast from one chemical, you get this. If you cast it from another, you get this. Okay, and this is what the dean had mentioned earlier. This is our electron tomography. Well, it's solvent inflatable. That's nice. Ideally, we want all the ionic regions which appear dark here, we want them to be contiguous. We could actually take something like this, we could expose it to solvent vapor, and within minutes, we could convert this to this. And so now we have all of these contiguous channels that could be used to pump CO2. Well, does it work? Again, using water as kind of a tracer here, we found that the solubility of water was higher in the block polymer compared to Nafion. We found that the diffusivity of water in the block polymer at higher relative humidities was higher than that in Nafion. All of this seemed to indicate that we should have a material that would be good at capturing CO2. And lo and behold, with assistance of a good friend, Maybrit Haig from NTNU, we found that, yes, we could get quite good CO2 permeability. And the fact that we could perform single gas and mixed gas experiments and get the same result indicated there was no plasticization occurring. So all of the CO2 was following the water, which was really good to know. Now, if you look at Nafion, well, it's a little bit better. So does this really get us anywhere? The difference is down here in the selectivity. For Nafion, the selectivity started to simply plateau off when we changed the humidity, whereas for the block polymer, it kept going up. So this gave us the inkling that maybe this approach was actually a good one. Then we found that not only water vapor affected these polymers, but water did as well. So this was what we got from the solvent vapor annealing, but now if we simply put the polymer, this polymer, into water, we started off with these mice cells, and we got this. And this is again a 3D TEM image just to show that this structure is highly complex, highly non-equilibrium, and highly connected. And that's what we wanted for our materials to, again, pump CO2. In fact, when we started taking these materials, casting them from different solvents to get different initial morphologies, and then looking at the behavior before submersion in water and after, we saw that there was no change in the selectivity, but there was considerable change in the permeability. And did this gain us anything? Yes. We started to cross over that upper bound. So this was promising. But it gave us, again, the idea that maybe water was the key. So now, if we move away from just simple solution diffusion, what if we added in the facilitated transport? This is work that was done with folks at SINTEF in Norway and NTNU. And now, what we're going to do is we're going to combine the two different mechanisms I told you about earlier. We're going to have facilitated transport, and we're going to have solution diffusion transport. Most polymer membranes from days gone by were self-standing. They were thick because they had to stay intact. Then they became very, very thin, but they needed a support. And that support is macroporous. So in that case, what we have is CO2, nitrogen, maybe some water vapor, and when these go through, there's not really a whole lot of difference between what goes in versus what comes out. There's a little bit of a preference for the CO2, so you'll see the arrow gets a little bit bigger down here and the nitrogen gets a little bit smaller, but overall, there's not a big difference. How is carbon capture conducted commercially? Not usually with just polymer membranes, but with large facilities. And these use absorption columns that are filled with amines, liquid amines. And these go through a series of unit operations so that eventually the CO2 is stripped out. The amine is recycled after removing the CO2. The CO2 is stripped out from the mixed gas stream, so the gases are left pure. The CO2 is stuck in the amine, it too is removed, and then the amine is recycled. The idea we had, what if we could take this and put it right on top? You've all heard of lab on a chip. How about plant on a film? So in this case, what we wanted to do was we wanted to use technology and put it right on the surface. And there it is. We essentially grafted polymer chains to the surface so that we could initiate our facilitated transport mechanism. And now this very, very, very thin layer, it's not a coating, it's a layer that measures on the order of about 10 nanometers or less. This is going to concentrate CO2 because there is water vapor present. And because it now concentrates the CO2, we have a lot of CO2 that can get through compared to just a little bit of the nitrogen. We call these hybrid integrated membranes. So here's the chemistry that basically starts off with simple hydrogen abstraction. We then use a UV technique to graft from this initiator site a polymer chain. We can then do a simple substitution to introduce the amines. And from surface analysis, we see that before, in both cases, we're looking at polydimethylsiloxane, a rubbery polymer, and polytetrafluoroethylene, which you might recognize as Teflon, but this is not semi-crystalline Teflon. It's the amorphous form. And this is already used in membrane technology. So if you look at before, there is virtually no nitrogen signal, and afterwards, we certainly have the appearance of nitrogen. Moreover, if we start looking at the topology, we can use low voltage, ultra high resolution scanning electron microscopy thanks to the AIF. And what you see is that before the modification, the surfaces are very smooth, but for the PDMS in particular, after the modification, even with the SEM, you can start to see a hint of the structure that forms. And then, of course, from AFM, which you see over here in the oblique views, you can see the structure has already developed. If you look carefully here, these are paired. This is a height image. This is a phase image. What this tells us is that these light areas are protrusions. The same regions over here as dark means they're soft. So we're essentially looking at groups of polymer chains that have been put on the surface. Most important part. Before we do any modification, those are the filled circles here, PDMS and the PTFE-AF. And you'll notice very high permeabilities, very low selectivities. Once we modify the materials, slightly lower permeabilities, but very high selectivities. So there's still a little bit of a trade-off, but we're getting to very high selectivities now. In addition to that, these are CO2 to nitrogen. What about methane sweetening? Here's PTFE, and this is where we can get to. Again, orders of magnitude improvement in separating CO2 from methane. Okay, so final slide dealing with this aspect. Here are the two starting materials. Here is the original upper bound. Here is that new upper bound, which is based on polymers of intrinsic microporosity. And now let's go ahead and step by step walk through what are all the relevant aspects of this. These are the best polymers used for carbon capture. Most of these are ethoxylated polymers. So they rely on some degree of a polyether along the backbone. In some cases, a few of these use graphene as well. Okay, but you see where they lie. Are these commercially viable? No. They're far too expensive to make. So what are the commercial materials? Right there. These are the three commercial membranes that are used currently for carbon capture. Where do our materials stand? Up here. So we can change temperature for PDMS and we can get it into the Goldilocks region. For the PTFE, it's already there. What's the big selling point to this? We're starting with membranes that are already used. We don't have to come up with brand new materials that are synthesized from a starting point. These PDMS and PTFE-AF are already used. So now it's just a matter of modifying the surface and introducing the facilitated transport mechanism. Okay, so all of this is really pointing towards developing materials to combat or mitigate climate change. There's something else about climate change that I overlooked that I think everyone should be aware of. And that is that environmental factors like climate change can also drive microbial outbreaks, such as the bacteria that have become prolific after Hurricane Ian. Or now we have reintroduction of frozen lakes that contain various microbes that could re-enter the ecosystem now that climate change is starting to melt away the polar ice caps. This sounds like something from a John Carpenter movie, doesn't it? But we don't have to look that far. 2016, first superbug to be identified in the US. 2020, superbugs being more worrisome than COVID. This one, from July of 2022, superbug infections spiked during the pandemic. Superbugs? Do they wear a little S on their chest? No. These are bugs, these are microbes that can be a little bit more dangerous than even what we encountered with COVID. COVID was an acute problem, as are all pandemics. Not to be underestimated, sorely responsible for many, many fatalities that could have and should have been avoided. But it's not the first, it won't be the last. We've had our share of different pandemics for many, many years. But it is an acute problem. It usually has a relatively short lifespan, although COVID seems to go on and on and on. Whereas the chronic problem, hospital-acquired infections, introduction of bacteria and fungi that become resistant to normal drugs, viruses that are capable of mutating and dodging our vaccines. These are the problems that continue. These are the problems that if you look at the CDC website, you start to get an appreciation of how much of a financial burden they place on just the American healthcare system. This isn't the world healthcare, which is, of course, more dramatically affected. So one of the things that we would like to start thinking about is a more continuous and active prevention route. Not just wearing face masks or PPE in other forms, but being far more active. Now you might say, well, these types of bacteria are very uncommon. No. If you look at MRSA right here, you'll notice that the United States has actually a fairly high tendency for MRSA infections, along with South America, Western Europe, Australia. So it's not something that is exotic. This is something that can affect anyone. Well, remember this guy? We talked about him a little while ago. And we know that it self-assembles, it forms a nanostructure, and we know that it has hydrophilic channels. What can we do with this? Well, I've shown you that it could be used for carbon capture. It can also be used for electroactive media. So what you see here is what's called an ionic polymer metal composite. And the only thing we're doing to this is applying a potential across it. Or, if you want to, we could put photosensitive dyes into this material and turn it into a solar cell. We could either try to mimic leaves, which is very easy to do, or we could put in some titania and we could make a dye-sensitized solar cell. And now we're looking at about 7% efficiency, and we're looking at materials that are self-adhesive, have all the properties of a thermoplastic elastomer, so they're actually quite good. And if you look at the incident photon conversion efficiency, you'll notice it picks up light over the entire visible light spectrum. So these materials have kind of a very wide range of applicability. But one that we didn't quite expect was that they could be used for antimicrobial properties as well. So along with Professors Galati and Scholl, who are kindly with us today, we started looking at this material because now we had a material that was filled with acid. What effect would that have on any microbes? Well, it turns out that the protons from those acidic groups can migrate to the surface in the presence of hydration and basically turn the water in contact with the surface highly acidic. What's highly? pH less than 1. Now, for many different types of bacteria, you find that at low pH, you can kill the bacteria or microbes in general. So this is MRSA, and you'll notice that over the course of 5 minutes, the population of MRSA went from 100% down to the minimum detection limit of 10 to the minus 4. That's a 6 log unit reduction. Okay, in other words, we're at 99.9999+% kill. These are the live dead assays to show that there is no surviving MRSA. If you decide that you want to instead use something like saticloth here, yes, it kills everything within 2 minutes. So we're talking comparable timescales here. The big difference is this is continuous. This is eco-friendly because it can be recycled. And this is rechargeable by simply introducing an aqueous acid. This, on the other hand, like a lot of PPE, winds up in landfills. And so we have tremendous solid waste problems. So if we look at the ESCAPE series, and I just wanted to point out, for those of you who are interested, the diffusivity of protons in just bulk water is about 1 × 10⁻⁴ square centimeters per second. We estimate that the diffusivity of the protons in our materials is on the order of 10⁻⁶ square centimeters per second. So there is a difference due to the fact that the protons have to diffuse through the nanostructure of the polymer. The escape series corresponds to those gram-positive and gram-negative bacteria that are most commonly encountered with regard to hospital-acquired infections. And they are denoted here by a red first letter. That's how we get escape. The only one we're missing is the P. But it gives you an idea of all the different types of bacteria that were checked. And in all cases, 5 minutes exposure time, we get down to the minimum detection limit. There's only one case where we had the polymer with only 26 mole% sulfonation that didn't kill MRSA down to that level. But the one at 52 certainly did in all cases. And I think you would agree with me that this is very close to 100% kill. What about C. difficile? C. difficile is an unusual bacterium because it's quite lethal, especially to the elderly who have just come off of antibiotics. According to the CDC, it has an urgent threat level. And it's also very personal to me because you might remember the picture I showed you of my mother. She went into the hospital with a diabetes infection. She never came out because she contracted C. difficile. So 6 days later, she was dead. This is an anaerobic microbe that can form a very resistant spore. And that spore is resistant to temperature, to UV radiation, even to chemicals. Well, we've examined how this material behaves on this block polymer, and you'll notice that in the vegetative state, not the spore state, we're looking at full inactivation, again, within 5 to 10 minutes. There are 2 different strains here. That's what the different colors refer to. The one that is in red is far more resistant than compared to the blue one. And this is what C. difficile looks like before inactivation, and this is after 5 minutes. And you can get a feel for how destructive this whole inactivation process is. Now, I've been referring to these as antibacterials, not antimicrobials. So for me to call it an antimicrobial, I need to demonstrate that it doesn't just kill bacteria. So let's consider now the case of viruses. If you cough or sneeze right here, and there is a droplet of liquid that contains viruses, well, this is what we think happens to the virus. It essentially dissolves on the surface. Now, these viruses can last for several days on different surfaces, most commonly metals and plastics, and that includes face masks. So, does this material work? Yeah, it does. Here are 3 different viruses, and you'll notice that once again, the polymers do a very, very good job for VSV virus and the influenza virus. For the human adenovirus, they're a little bit more resistant, but nonetheless, we do see an antimicrobial efficacy. But I think most of you are probably more interested when I say virus. You're probably thinking about the one that we just had to deal with. So this is coronavirus. This is SARS-CoV-2. And you'll see that within 5 minutes, we get to the minimum detection limit. And we do that at all of these different times. The reason why there are differences in the minimum detection limit is because the starting suspension concentrations were different. That's all. But it does work quite well. And now compare that to copper. We all have heard how copper is great for killing bacteria. It is. For viruses, not so much. You can get to this level of inactivation after 4 hours, that's actually comparable to some cationic polymers, where you could get to some level of inactivation after about 4 or more hours of exposure. Here we're talking minutes. So we're talking a considerable difference in time scale. Is this a general approach? Well, we looked at not only this polymer, but this polymer and this polymer. All the blue indicates where it's been sulfonated, and you can see in all cases, as long as we had sufficient sulfonation, we saw that they all worked. And the reason why I show this is because it has been an accepted paradigm in polymer science that we use cationic polymers to kill microbes. This says anionic polymers can work too, as surfaces, not in solution. And by the way, this is devoted to a different virus. To do the SARS-CoV-2 test, we collaborated with the National Emerging Infectious Disease Laboratory up at Boston University, because they had a BSL-4 facility. To do the test here, we have a BSL-2 in Professor Scholl's lab, and so we wound up using human coronavirus 229 echo, which is responsible for the common cold. Is this idea a general paradigm? Can we simply say all anionic polymers are capable of forming these highly effective antimicrobial materials? Well, if they are structured, that's the key to these. Because in solution, there's a large wealth of information about how anionic polymers can be used as antivirals. But what if we went back to something that you've seen before? Nafion. It has these hydrophilic channels. They're smaller. It has sulfonic acid groups. So it has available protons for transport. Would this work? And the answer is yes, it does work. It doesn't necessarily work as effectively, it doesn't get to the same level, the same minimum detection limit, but it does reasonably well over about 30 minutes. So yes, this idea seems to be now a general paradigm, not specific to a particular material. The dean had mentioned early on that part of this award is based on extension. So I wanted to share with you how this is now being used. So this particular mechanism is already it's patent pending, but it's also exclusively licensed. And it has received last year emergency approval from the EPA so that it could be in fact used by Delta Airlines. So if you went on a trip and you were using a kiosk, or if you were touching a ticket counter, you were actually touching this material. And it was disinfecting your fingers, as long as there was some degree of hydration present. That was always the key. It doesn't work when it's dry, but it does work when there's hydration present. So, I've given you 2 examples of where we've used water-activated polymers to try to address global challenges. Now, the most important part, the thank you. So first, to the dean, thank you so much. And Louis, we are going to miss you. Secondly, for my student collaborators, my faculty collaborators, and all those who have given me the chance to be creative and disruptive, and I point out in research, I don't want to be disruptive other ways, but I enjoy coming up with new solutions that could be potentially impactful. and most importantly, for giving me the chance to learn, because I am a strong proponent of lifelong learning. And this has been a wonderful opportunity for that. The university, for giving me the opportunity to contribute to society through my research, to teach the next generation, serve as a role model. And just recently, I've had the opportunity to kind of look back over my shoulder and see how much of a privilege it has been to be at NC State. Of course, could not have done it without these people. So, my lovely wife, who is right here, who has always stood behind me and given me all the support and love that I've needed over the years. My 2 kids, as they go off exploring around the world. And of course, the 2 little guys over here who are probably asleep right now. And of course, I could not have done this without divine inspiration, and I'm most grateful for that. So thank you so much for your attention, for this opportunity, for this award, which again, it isn't for me, it's for the students who and the collaborators who have worked with me. And I thank you all for your time.
Thank you very much. No, you stay up there a second. We have some time. We don't have to rush here. Does anybody have any questions or comments for Rich? Other than where are we gonna find that thing at the end that you said you could put on surfaces and stuff, right?
That is actually, well, I don't know how much of that I should talk about, Chachi.
No, that's okay. Don't worry. Everybody's not leaving you.
It's in the process, let's put it that way. So there are efforts to make it more generally available. Yes?
Yeah, Dan?
My understanding, first of all, thanks for a very interesting talk. My understanding of a lot of the deployment, or maybe most of the deployment of technology to remove carbon dioxide is really to reduce emissions, to clean things up before they're emitted. But I increasingly thought that people would just clean the air and use some techniques like this to just remove carbon from the air. Is that feasible, and would any of these technologies speak to that?
That's an excellent question. So these membranes are really designed to scrub out, so to speak, the CO2 from emission streams. What you're talking about is atmospheric carbon capture. And there are a lot of efforts and a lot of different strategies for trying to achieve that. And I'm actually working with a company right now for exactly that purpose. It uses a very different approach because the volumetric throughput of atmospheric gases has to be incredibly high, and the materials have to be sufficiently robust so that they can not only capture the CO2, but unlike what I've shown where we're capturing CO2, removing it, these other approaches just capture it. Then they use either a temperature swing or a pressure swing to remove the CO2 and capture it that way. So it's a slightly different approach. It's actually more in line with the liquid amine absorption idea than using polymer membranes. That's a great question.
Any other questions? Well, Rich, congratulations and thank you very much.
Thank you.
You see, we have a little reception in the back, is that correct?